Well, thanks for having me. It's a pleasure to actually be here in person. So there was a talk, I hope some of you remember, by my student Osmond a couple of weeks ago, where he talked about the information paradox, kind of give an introduction. So I won't be reviewing the information paradox under assumption that you all remember every last detail of Osmond's talk. My talk today is really about the recent developments since 2019. So I'll be focusing mostly on black hole information in holography, ADS-CFT, which I'll review. I will say a few words at the end about how we go beyond ADS. So if you have questions about that, you could ask them in the middle, but keep in mind that I will be talking about that towards the end as well. And yeah, this is part one, and they're going to talk about computing the page curve, the curve of entropy that goes up and then comes back down. We have unitary black hole evaporation. Time permitting, we'll talk next time about computational complexity and the Hawking radiation. Maybe a slightly ambitious or optimistic plan. So, all right. So I will give a bit of an overview. I will remind you very briefly about black hole evaporation and the page curve. And that's sort of a rough overview of what we set out to do in 2019 that resulted in a renaissance in the black hole information paradox. And I'm going to spend sort of most of the time talking about the holography of evaporating black holes. It turns out that it's not so simple to make anti-de Sitter black holes evaporate. And so there's a little bit of subtlety involved in how we do that. And also discuss holography itself and ADS black holes, how we handle that. And then I'll talk about how we compute the page curve, how we actually are able to use tools from semi-classical gravity rather than from full non-perturbative quantum gravity to see the evidence that black hole evaporation, at least in this context of holography, is in fact unitary. And I'll sort of give a brief preview of the role of complexity and why that's going to be the subject for Friday's talk, assuming we get there. All right, so brief reminder of black hole evaporation process. So here we have a 3D diagram of an evaporating star. So the T before here corresponds to a time before the black hole is formed. We just have some stars, sphere. Doesn't have to be in spherical symmetry, but for simplicity, let's take it in spherical symmetry. This collapses, we get an event horizon. In the interior, it keeps on collapsing until we get a singularity. This is sort of, if you prefer, you can think of this as sort of standard Eddington-Finkelstein coordinates. Now here I've illustrated a particular time t during. This is once the event horizon has started to shrink as the black hole evaporates due to Hawking radiation. This red line here is the event horizon, the intersection of the event horizon with this moment of time. So time here runs upwards. Eventually, so this regime here, the black hole is still large enough that we expect small curvatures at the event horizon. So we expect that effective field theory, that is quantum field theory weakly coupled to general relativity, is still a good description of the space-time near this red surface over here. Now, as the black hole gets progressively smaller, eventually we expect that we're going to lose control of effective field theory and the semi-classical approximation. Again, when I say the semi-classical approximation, that assumes that there's a small parameter. The small parameter here is going to be G Newton multiplied by H bar. That's the semi-classical parameter. We say when that parameter is small compared to other scales in a problem, then we say, all right, that's well described. It should be well described by a weakly coupled limit of gravity with quantum field theory, various quantum fields propagating in our space-time. So this, again, Osmond talked about this last time. I'm just reminding you, this is the general picture we have of black hole evaporation. All right, so now one of the things that Osmond also talked about is the sort of litmus test that we have for determining whether our evaporation process is consistent with unitarity of quantum mechanics. So if the black hole evaporation process were consistent with the unitarity of quantum mechanics, then if the initial state is pure, that means it has zero entropy, then the final state has to be pure as well. In particular, that means, so here we're looking at the von Neumann entropy of the radiation. So when we start out, we're looking at, this is a pure state for the whole system. This is before the black hole is formed. You could say the radiation is the empty set. Say, okay, well, that's going to have zero entropy. Eventually, we're looking at something where the radiation is the entire system. Again, that's if evaporation is unitary, that's going to be a pure state, and the entropy will go back down to zero. In the meantime, here, the radiation is a subsystem. It's part of the system. That means that it is allowed, and in fact, it has to be larger than zero. So we expect starting out here, in the beginning, radiation entropy will begin to increase. Eventually, it has to go back down to zero, so there's going to be a turnover at some point. And as sort of very rough reasoning, Page actually computed what it has to be if the evaporation process is unitary. He sort of said, okay, well, at what point does this turnover have to happen? Turnover has to happen approximately when the black hole has radiated more than half of its mass. And he gave predictions for basically roughly what this has to do, treating it like an ordinary quantum system. If it were an ordinary quantum system with no information paradox, he gave predictions for what this shape would look like. Not just that it goes up and comes back down, but more the slope and the turnover here. Of course, this is the regime where we expect strong, non-perturbative quantum gravity. That's this regime right here. So we don't ever hope to have a semi-classical control of what goes on there. But up until somewhere over here, we certainly expect to be able to have effective field theory be valid. And of course, the fact there's a large gap between the prediction of Hawking's calculation and the semi-classical and the unitary prediction, even in a regime of effective field theory, is in a nutshell the information problem. So this is a very brief lightning primer, a reminder of Osman's primer on the information problem. All right. So what is the goal? What is the goal in our 2019 paper? So the goal was to compute the Page curve in a quantum theory of gravity. And why is that the goal? Well, if we can compute the Page curve in a quantum theory of gravity, then maybe we'll be able to understand where does this gap come from, given that we expect that the effective field theory is a good description of this space-time.
So do you mean a complete quantum gravity theory, or?
So ultimately, that is, of course, the goal. Now, what was the miracle, I would say, is that we actually ended up being able to do it in semi-classical gravity, which was unexpected. The conventional wisdom prior to 2019 was that you just can't. If you wanted to see a curve that goes up and turns back down, you had to keep track of non-perturbatively small corrections, and somehow magically, those would add up and give you this large gap. And of course, it's very odd and very difficult to understand how that would happen, given that those corrections are all non-perturbatively suppressed. But if we think that quantum gravity is unitary, then it should give us an answer. Now, again, the miracle actually turned out that we didn't need to work with non-perturbative quantum gravity in order to see the Page curve. And of course, that sort of answers number 2 here, understanding whether this computation of the Page curve in a quantum theory of gravity implies some kind of a breakdown of effective field theory at the event horizon, which would tell us indeed that even though we think effective field theory is valid, actually there's something really special about black holes that the event horizon actually, in the equivalence principle, basically we have to give it up. Event horizon is a very special place, and you can actually tell when you cross the event horizon, which would of course be very disturbing from the perspective of general relativity. So if we hope to do 1, and of course answer 2, we're going to need a formulation of quantum gravity. This is, we always thought, okay, in order to compute the Page curve, we need to understand quantum gravity better. And we need a description of black holes in that quantum theory of gravity, which is where holography comes in. So holography is a quantum theory of gravity. It may not be the only quantum theory of gravity, but I would claim that it is our best understood quantum theory of gravity at the moment. So, oh, sorry about that. This is 2 figures now. Okay. All right, so let me pull this to the side so you can see this, sorry. Great, all right. If you can ignore this. Okay, so what is ADS-CFT, also known as holography, also known as gauge gravity duality? It is, I would say it's a formulation of a quantum theory of gravity. It is a dictionary between quantum gravity and anti-de Sitter space, which you can think of as an infinite box with reflecting boundary conditions at infinity. That is dual, that is described completely by a particular type of non-gravitational quantum field theory in one lower dimension. So here we have these two pictures. We call this the bulk. Quantum gravity lives in the solid cylinder inside the cylinder. And we call this the boundary. It's a non-gravitational quantum field theory that lives on a boundary of a cylinder. Now I want to emphasize here, this quantum field theory doesn't actually live on the boundary of the bulk. Okay, there's no quantum field theory living at infinity. It lives on a copy of the asymptotic boundary, not in the same space-time. So quantum gravity in anti-de Sitter space is completely described by non-gravitational quantum field theory. That allows us to then say, okay, this non-gravitational quantum field theory, typically something supersymmetric, is a complete and total description of non-perturbative quantum gravity with anti-de Sitter boundary conditions. So if we can understand the dictionary that relates quantities, observables, data in quantum gravity to quantities, again, observables, information in the non-gravitational quantum field theory, then, well, any calculation we can do in quantum field theory, we can do in quantum gravity. So this relation here is incredibly powerful, as you might imagine. So here it is in written language. So it's a dictionary. I like to think of ADS-CFT as a dictionary, a way of getting insight into quantum gravity. It relates quantities in quantum gravity to quantities in non-gravitational supersymmetric quantum field theory with a UV fixed point, conformal field theory, usually. Now, I don't want to claim that quantum field theory is something that we understand really well. Quantum field theory is hard. There are a lot of things we don't understand, various topological properties, anomalies, symmetries, discrete symmetries. There's lots of things we don't understand, but we definitely understand it a lot better than we understand quantum gravity. And so we can do calculations in it. We know what kind of animal it is, we think. So again, this gives us good insight into quantum gravity. The more we understand quantum field theory, of course, as it turns out, the more we understand quantum gravity. And I really want to emphasize the fact that this tells us that quantum gravity is nothing more than a quantum field theory. And that gravity is somehow encoded in this quantum field theory, but at the end of the day, it's just a quantum field theory. So how do we use this to talk about black hole evaporation, to understand the evaporation process, to talk about the page curve, to think about unitarity? Well, for black hole evaporation, up until we get pretty close to the evaporation point, we're going to want to work in the semi-classical approximation. So again, we want to work in a limit of ADS-CFT, where quantum gravity, it becomes approximately semi-classical. So that means we take the limit where G Newton H bar goes to 0. We do a perturbative expansion in G H bar. So that's the limit where the curvatures are not strongly interacting with our quantum fields. Again, this is the limit where we expect that we still see a large gap along the page curve between the unitary process and the non-unitary process. So again, we'll be working with a perturbative expansion in the small parameter G in the bulk. And just as an aside, moving forward, I'm going to be a particle physicist and work in units where H bar equals to 1. I could be a relativist and work in units where G equals 1, but I find it's not standard in the field, and I'll definitely make the mistake of just, I can't not set H bar 1. Sorry, it's just not going to happen. Okay, so what is the corresponding limit in this dictionary to the dual quantum field theory, the one on the boundary? Well, that of course corresponds to quantum field theory at large de Hooft coupling and with a large gauge group. So we're working with an SUN group and so the large N limit. These theories have very nice properties that some of which we can understand. The fact that these theories are typically conformal also means that there's some quantities that are independent of coupling, or that we understand how they transform as the coupling changes. So again, this is a limit of the quantum field theory where we do understand a decent amount. Great. Okay, so there is one immediate implication of holography for black holes. A black hole in anti-de Sitter space is just an ordinary non-gravitational quantum system, because quantum gravity is nothing but an ordinary non-gravitational quantum field theory. And a black hole is just a state of quantum gravity, which means it is just a state of an ordinary non-gravitational quantum field theory. So here we have a black hole in the bulk. You have a bunch of strings lying around if you're working with string theory. And this is the hologram in one lower dimension in quantum field theory. So it's just an ordinary state, some fluctuations, maybe it's thermal, maybe it's not. But the point is, it's just an ordinary non-gravitational quantum system. Yeah.
Just to clarify, when you say, you said a couple of times quantum gravity is nothing but a quantum field theory, this is conditioned on being yes, right? Having asymptotic yes.
Yes, it is. Mhm.
We don't know for a fact.
Oh, absolutely. Yeah. This is conditioned on it being innate. Yes, that's right.
A related question, you said you want to have reflecting boundary conditions at some point, or
What, sorry?
reflecting boundary conditions? Is this assumption also necessary? Because in principle, I could play all sorts of other conditions.
Good. So this is something that will actually exploit the fact that we can change the boundary conditions in order to force an ADS black hole to evaporate. So I will get there. Yeah. Okay. So in particular, since we have this an ordinary non-gravitational quantum system, it evolves unitarily. This tells us that the dynamics of anti-de Sitter black holes is unitary. So again, I'm really reiterating this point, but let me just make it quite clear. A black hole is an ordinary non-gravitational closed quantum system. And non-gravitational quantum systems that are isolated evolve unitarily. In particular, there's no process that we know of that can make an ordinary closed quantum system evolve non-unitarily simply by the laws of quantum mechanics. So that means that black holes in ADS must evolve and evaporate unitarily. And so it appears that ADS CFT has solved the problem by its mere existence, right? So are we done? That's it. We're done. This black holes evaporate unitarily. We're not quite done. There are multiple reasons why this is not quite enough and not quite satisfactory. So sure, this gives us an indirect answer that black holes evolve unitarily, but how? This doesn't address for us this large gap between the Page calculation and the Hawking calculation. It tells us that quantum gravity preserves unitarity, but it doesn't tell us how. It doesn't tell us whether effective field theory actually does break down at the event horizon or near the event horizon in a regime where it has no business breaking down. So it's great to know that, okay, information isn't really lost, at least in ADS, but we kind of want to know how that happens. And there's also what I call conservation of misery here. So as was a recent question here, ADS boundary conditions are reflecting. So that means that if you have a black hole in ADS and it radiates, the radiation goes off to infinity. And because light rays in ADS, it takes an infinite amount of atom parameter of finite time, they actually reach the boundary in finite time and they bounce right back. And so that means the radiation comes out, but then it's going to collapse right back in. And the black hole doesn't actually get to evaporate fully. It just sort of reaches equilibrium with its radiation, which is constantly bouncing off the boundary and coming back in, unless we have a really small black hole, meaning the black hole evaporates before the radiation has a chance to bounce back. So bouncing, the time it takes a light ray to go off to the asymptotic boundary and bounce back is one light crossing time in ADS. And we need black holes to evaporate in ADS. We need black holes that manage to evaporate in less than one light crossing time. And as it so happens, these are exactly the kinds of black holes that don't understand in ADS CFT. So we only understand the holography, the dictionary, the ADS CFT dictionary for large black holes in ADS that do not evaporate because they just achieve equilibrium with their radiation. So this is, those who are familiar with the Hawking-Page phase transition, this is really the fault of Hawking and Page for having discovered this. So it turns out that the dominant contribution to the path integral, the partition function, is not dominated by, so that contribution is not ADS black holes for black holes that are very small, but rather what's called thermal ADS. So the point is that we don't understand the holography of small ADS black holes, so they may evaporate, they may do interesting things. All we know is that it's unitary. We can't extract more information from that. Yeah.
So this limit, which is hard to understand.
Yeah.
is it the dictionary that's breaking down or just the quantum field theory itself you don't understand?
It's really not neither of the above.
Okay.
What's happening is, so in ADS-CFT, we have some quantum field theory state, or we have some state in quantum gravity in the bulk, and we'd like to understand its dual. Now, the way that we typically do this is we try to prepare the state using the path integral. And we write down, I'll actually do this in a little bit. We write down, we say, okay, the partition function of the theory is given by some path integral over the set of all metrics with certain boundary conditions. But of course, we can't do that path integral. We have no idea how to integrate over all metrics. So we do a saddle point approximation. We ask, what's the dominant, basically WKB, you ask, what's the dominant contribution to this path integral? And as it turns out, small ADS black holes are never the dominant contribution. So what happens is we say, okay, we have some quantum field theory state, we prepare its bulk dual from a gravitational path integral, and it's never the small ADS black hole. So that's the problem. It's a subdominant contribution. And that means that in this semi-classical approximation where the saddle point approximation is valid, we can't actually compute things in the bulk and map them to things in the boundary because the bulk is not a small ADS black hole. It's what's called thermal ADS. Essentially, this is a matter of temperature. When ADS is kind of for sufficiently hot temperatures in the dual quantum field theory, for thermal state is dual to a large ADS black hole. But when your quantum field theory state is not so hot, it's actually dual to what's called thermal ADS. So that's the issue here. It's not that anything breaks down; it's that there is it's a subdominant contribution to the path integral.
Maybe this is the same question, but in your reason number one, why would you even suspect that EFT would break down the event horizon?
Because that's naively the only way to explain the large gap between the Page curve and the Hawking curve. It's an order 1 gap, which means that the predictions of semi-classical gravity and quantum gravity differ by order 1 in a regime where they should only differ by e to the minus g. E to the g.
It's basically the gap between unitarity and Hawking.
Exactly. Yeah, that's a large gap. And so since we expect quantum gravity in ADS to be unitary theory and Hawking's calculation in ADS essentially, if you can make a black hole evaporate in ADS, which we'll do shortly, Hawking's calculation goes through the same way. Then you run into this problem where you have a large gap between the predictions of two theories where that should be only non-perturbatively different in this regime. So the question is, if quantum gravity is right, then we say, okay, well then that means that semi-classical gravity is getting the answer wrong in a regime where it should be a great description of physics. So that's a breakdown of effective field theory.
Is there also an argument from the NPS that if you want to preserve unitarity and no drama, then
Yes,
it suggests that EFT breaks it?
that's right. Yeah. There are multiple arguments that information conservation suggests that you have to have effective field theory breaking down the horizon. Now, what we'll see here is actually in the cases that we studied, and I can talk more about whether those are typical or not. You actually can get semi-classical gravity to be valid, but reproduce Page curve. And I mean, I have my own hypotheses on how to interpret that from the perspective of typical states and so on, which I'm happy to talk about, but I think that's going to be fun, food for thought on Friday. Okay, so to answer all of these questions, really, we have to understand black hole evaporation in ADS. So we either have to try to understand small black holes, or we have to find a way to force large black holes to evaporate. Now, we decided that the holography of small black holes is just way too hard. So instead we said, let's try to force a large black hole to evaporate instead. So the way we do this is we take a large ADS black hole and we essentially just couple the quantum fields in the bulk to a cold reservoir, meaning to a quantum field theory in its ground state. So it's essentially what that results in is a flow of energy from the hot black hole to this cold reservoir. It's a natural way of taking the Hawking radiation and pushing it off into an auxiliary system. so that it doesn't get a chance to bounce off of the asymptotic boundary and come back into the black hole. There are many ways one can achieve this. One of those ways is by imposing absorbing boundary conditions at the asymptotic boundary, so that the Hawking radiation goes off and at the asymptotic boundary gets absorbed into another external system. So but we have to be careful here, because now we have two subsystems in the problem. We have the bulk in ADS and we have the reservoir. So in computing the page curve, we have to remember that it is the entropy of the whole thing, the reservoir plus the black hole, plus the entire ADS that we expect to go to zero at the end of the evaporation process. So I should say this mimics black hole evaporation in asymptotic flat space. And in fact, one thing that you can do, you can even, in certain cases, this doesn't always work, but you can even imagine you have an ADS black hole from collapse, and this was the ADS boundary. Say, okay, this has reflecting boundary conditions for a while, and then at some point, we actually are going to take a CFT in its ground state on flat space, and we're going to glue it to the asymptotic boundary here. And here we're going to have transparent boundary conditions. So the radiation that comes out is going to keep on going. Now, this is non-gravitational here. So it's only mimics flat space. It's not exactly, this looks like an asymptotically flat black hole. You have to keep in mind there's no gravity here. So it's a toy model. And of course, there's issues with gravitons and factorization of linearized quantized gravitons that we're not going to worry about now. But this is, in some sense, people are very excited about this because the sense in which this is giving a square plus to the to an evaporating black hole. So this is one way to do this. It's not the only way. We can also just take these quantum fields and couple them in some non-geometric way to an auxiliary reservoir. So now there are many different ways to do this, as I just said. We can couple the fields in many different ways. In fact, one of the things that we showed is that it's fairly independent of the way that you choose to couple the two quantum field theories. The quantum field theory in the bulk, so we have some quantum field theory here. So the way that we choose to couple the quantum field theory in the bulk to the quantum field theory in the auxiliary reservoir, it's kind of immaterial. It doesn't really matter for the purpose of what we're going to show. We actually showed it's universal. The details of the coupling are don't matter at all. Now, of course, you can say all this, but could Martin's camera be pointed at the picture?
I don't think that's the camera.
Oh. Yes. Is that good?
You can lean it down just a tiny bit.
That's great. Thanks ever so much, because we can see the slides anyway. That's brilliant. Thanks.
No,
Nope. All right.
yeah, that was good.
Okay, cool. Okay, so as I mentioned, there are many ways to do this, but the point is that we actually want to do a calculation explicitly in order to make sure that this actually works. So where is this easiest to do? Well, it turns out it's easiest to do this in two-dimensional dilettante gravity. As 2D gravity plus a dilettante to make sure it's not sick, because of course 2D GR is a very slick theory with negative degrees of freedom. And we have perturbatively interacting conformal fields in the bulk, which is quantum field theory. You can think of with scaling invariants that we can actually add in a file rescaling, and we know how everything transforms. That gives us a lot of power in the sense of being able to compute the entropy of intervals in the flat space by applying a file rescaling. So that's the sort of the reason that is very useful to work with conformal fields in the bulk. For those who thrive on seeing Lagrangians, this is the action of the theory. So this is this topological term, JT gravity. This is the dilettante in JT gravity. That's where all dynamics comes from. And here we have the quantum field theory in the bulk. And this is the boundary dilettante. Oh, sorry.
That's right.
So now you might say, this seems really crazy why you're working with two-dimensional gravity. We don't live in a two-dimensional world. Well, it turns out that two-dimensional gravity is actually obtainable as a dimensional reduction of a high-dimensional theory, meaning you take all the spheres in 2D gravity, then a black hole in 4-dimensional gravity, a charged black hole, and you can have a separation of scales between the size of the spheres and everything else. then the dimensional reduction will actually give you exactly this theory, including the action of the conformal fields if your black hole is charged. So this can be thought of as an avatar for a four-dimensional theory of gravity. All right, so let's talk about the boundary equation.
Is it equivalent to that, or is it a simplified version?
So good. It is equivalent to it if you are working with spherical symmetry. If you are not working with spherical symmetry, if you have, if you imagine you take a spherically symmetric black hole, a magnetically charged black hole, and you throw in some shear, so you violated spherical symmetry, then it's not equivalent.
What about spin?
So, sorry?
Spin,
S-
is a Kerr black hole eligible?
So spin is fine. Depends on the spin. If you add in some freeform field, then we're going to have a problem because we want to be able to do a dimensional reduction. So we want to have a tower of fields where only the lowest ones actually matter, which is where we sort of inherit that. So it's a sector of the 4D theory. It's not equivalent to it, but it is obtainable from it. Yeah, it's a limited version of it, shall we say. Okay, so what's the dual theory? In the dual theory, we have what's dual to this part of the ADS part of this. So if this is 2 dimensions, then we have some Q of T1 in 1 dimension. It's dual to this. It lives on the boundary of the 2-dimensional cylinder, which means it just lives on a line.
Yeah.
Oh yeah.
Thanks, sorry.
Don't worry about it. Don't worry about it.
Maybe you should just skip that.
Right, right.
Right, and it's coupled to this CFT here. That's here in this, I think, in Cosmos space. Okay, so we have these 2 subsystems together, they constitute the entire system. And we can identify this with the radiation, since all of the radiation of the black hole ends up in this Minkowski CFT.
I have to stop sharing screen and reshare, so I don't think it's worth the hassle of something might happen.
I mean, because I just took a picture at the end and maybe attach it to whatever.
Sure. Yeah, good
Yeah.
idea. Let's do that.
Okay, so now again, as I just said, the reservoir is at a lower temperature, so everything is going to flow into the reservoir. That means we can identify this with a Hawking radiation. Now, the way we expect things to work then is that the Hilbert space of this is going to get progressively larger as more and more degrees of freedom from the Hawking radiation flow into this CFT here. So, okay, so that tells us that this subsystem is getting progressively larger. And so we expect that we indeed get something like a Page curve if this behaves unitarily, which is just 2 random quantum systems. No problem with them if we just look at these 2. It's just that this one is going to be progressively more of the system and this will be progressively less of it. So we expect that we get something like a Page curve like this from the boundary picture. All right, so now what happens in the bulk? Well, we found a way to force a large ADS black hole to evaporate as this auxiliary reservoir. And we know that this follows the Page curve if we don't think about holography, because it's just 2 quantum systems and they both behave like ordinary quantum systems. Now, if we do go to the bulk picture, then the change in this, the Page curve, is the consequence of the Hawking radiation moving from the interior of the bulk to the asymptotic region in that picture over there. So again, we can identify the reservoir with the radiation. The von Neumann entropy of the reservoir, we should identify with the von Neumann entropy of the radiation in the holographic picture. And again, this tells us that the radiation is going to follow the Page curve, but we sort of already knew that, right? The bounded picture is just ordinary quantum field theory. The question here is whether there is a way for us to use the ADS CFT dictionary to do a quantum gravity computation and see the Page curve. That's the question. And the answer is yes. So I guess it's I'm good to continue. Okay, all right. I would hate to stop now. It's kind of the punchline. All right, so let's compute the Page curve. How do we compute von Neumann entropies in ADS CFT? Well, in the case where we're working with two leading order in GH bar, put the H bar back in here, then we have this beautiful formula of real Takanagi and inhibiting Rangamani Takanagi. This is for static spacetimes, for dynamical spacetimes, that relates geometric objects in the bulk. In this limit, this is a purely classical bulk. There's no quantum fields anywhere. This is purely classical general relativity. So in this limit, we have this beautiful picture of RT and HRT, the initials of these people, which tells us the following. If we're given some asymptotically ADS spacetime, everything is classical, general relativity, no complications. The von Neumann entropy of the holographic dual to leading order, again, this is everything just to leading order, is the area of the surface X over 4G. So those of you who are familiar with the Bekenstein-Hawking story will identify this as the Bekenstein-Hawking entropy of a black hole, where X is the area of the event horizon. Now, in general, X will not be the area, it will not be the event horizon. In general, it's going to be a local extremum of the bulk area of functional. What that means, if you take the surface X, slightly wiggle it around, then in terms of the wiggle, if you perturb it a little bit, to leading order in the perturbation, the area of X won't change. It's a local extremum in the area. We call this an extremal surface. And there's one more requirement, which is that there has to exist a hypersurface H, whose boundary is the union of X with the Cauchy slice of the asymptotic boundary. So in particular, I draw a picture. Actually, I'm going to have a picture in the next slide, so do not do that. There's a picture in the next slide of this. So if there's more than one surface X, then we take them on the smallest area. So we may have multiple such extremal surfaces satisfying this condition. We'll pick one with if that's the case, then we say, okay, we'll take them on the smallest area. This is a consequence of the saddle point approximation again. We pick the one that dominates, which happens to be the one with smallest area.
What is I?
This is I is Scry. Sorry, there was no. I forgot to put the math Scry package in my tech code. Yeah.
Thank you.
So what happens in a single-sided black hole? So suppose we have a black hole formed from collapse, and we ask, okay, what is the? So we have some asymptotic infinity out here. We ask, okay, what's the extremal surface that computes the area, computes the entropy? Well, it's actually the empty set. This is a pure state. Its entropy is 0, and the extremal surface is the empty set. What about ADS Schwarzschild? ADS Schwarzschild has two asymptotic boundaries, and we can ask, what is the entropy of this one, or the entropy of that one? Now, in the CFT, this is actually like an EPR pair. These two sides are entangled. You expect the entropy of one of them is not 0. And indeed, the entropy of one of them is actually computed by the area of the bifurcation surface of Schwarzschild. That is the minimal area extremal surface. And this hypersurface business, there's a hypersurface right here, like this, whose boundary is the union of a Cauchy slice, Scry, and X. So this is the story at leading order in G. Now, what about the next order? Well, what happens in the next order in G is we have quantum fields propagating on our spacetime, but they're not allowed to interact with gravity. So this isn't quite the regime of evaporating black holes, where the black hole shrinks as a consequence of evaporation and radiation. There, the quantum fields are allowed to interact with gravity, just perturbatively, but it's still allowed. This regime, the order G is 0, as the next to leading order. That's a regime where we actually don't have interactions, but we do have quantum fields in the problem. And so this was proposed by Lefkowitz and Moldacena, where it's basically the same formula, the same surface X. So here's our X, but we now add a correction term. It's the von Neumann entropy of quantum fields outside of X. So just like when we compute the von Neumann entropy in any other scenario, we ask, okay, let's trace out the degrees of freedom inside of X and compute the von Neumann entropy of quantum fields in its exterior. And this quantity is very famous. It was defined by Jacob Bekenstein back in the 70s. It's called the generalized entropy. All right, but that's not quite what we want. So, I should say, so here's our single-sided black hole. The important thing is that for Lefkowitz Moldacena, the surface is the same. It's still this extremal surface X, it hasn't changed. That tells us that In this case, in this same case with the single-sided black hole formed from collapse, the surface is still the empty set.
So what do
Yeah.
you mean by single-sided?
Sorry, this should be a dashed line here. So a single-sided black hole, like a black hole formed from collapse, as opposed to Schwarzschild, which has two asymptotic boundaries.
Oh, okay.
Okay, so we want to talk about black hole evaporation. We need to go to at least the next order, ideally all orders in GH bar, any finite order in GH bar. And so fortunately, we do actually have that. This is work by myself and Aaron Wall from 2014. So now it looks almost the same, this formula, but you'll notice it's a chi here instead of x. This surface chi is different from x, so we call it quantum extremal. How is it different? Instead of being an extremum of the area, again, when you slightly perturb the surface into leading order in the perturbation, the area doesn't change. This is going to be an extremum of the sum of these two. The sum of the area of the surface and the entropy of quantum fields outside of it. So that means that as you slightly perturb the surface, the generalized entropy does not change to leading order. The area might change, this entropy might change, but the sum will not. So this is what we're going to use. This is to all orders in GH bar, any finite order. And this is what we're going to use to compute the von Neumann entropy of the radiation. Now I can pause here or I can continue to the actual calculation. Yeah.
Question. Without a theory of quantum gravity, what would establish that?
Good. So maybe you can hold on to that question. I have a slide on that. It's just say to answer your question very briefly and then answer it a little bit more detail later. It's any quantum theory of gravity where we can use the gravitational path integral in the saddle point approximation to get good answers about the semi-classical limit. So far I've presented it as if it comes inherited from EDS CFT, but as it turns out, you can justify this from the Euclidean path integral.
Netta, just a quick clarificatory question. Could you talk a little bit more about the selection process for this surface? You said it was minimizer at first. I understand that now we're talking about a different quantity that's being minimized.
Extremized.
Sure, extreme.
Yeah.
But it seems to be a space-time picture. So am I to think that I'm allowing myself complete freedom in where I'm anchored on the time-like boundary?
That depends on whether you're computing the entropy of Scry in its entirety or a subregion of it. So I could compute, there are really three cases here. So case one is where I'm interested in computing the entropy of a complete Cauchy slice of Scry. Then you say, okay, I don't actually care where the surface is anchored. You might worry that the surface could be causally separated from that Cauchy slice. And if that's the case, you could turn on some causal perturbation and allow it to propagate, change the area of the surface, which would correspond to turning on some unitary and modifying the von Neumann entropy, which is forbidden. But you can actually prove, physicist level of rigor, that the surface is always going to be achronally separated, or even achronally separated, generically acausally separated from the entire asymptotic bound. So in general, you expect there's going to be some event horizon, and there's going to be a region which is acausally accessible to the asymptotic boundary. That's case one. Case two is you take a subregion of the asymptotic boundary, in which case the surface has to be anchored on this subregion. Now, case three is the evaporating black hole. Things are a little bit complicated there because the entropy changes depending on which slice you take. The entropy computed with respect to this is different from the entropy computed with respect to that. So in that case, you sort of have to look for surfaces that are acausally separated from that in the bulleted patch. So the rules are essentially the same. You look for surfaces acausally separated. In this case, you don't have to impose it by hand. It's always true. In this case, you have to anchor it. In this case, you have to impose it by hand.
All right, thank you.
Sure. Should we pause here for discussion, or do people want me to continue?
How long would be the last slide you want to get through, or last two or three slides you want to get through?
I can You know, why don't I wrap up the calculation? Maybe another 5 minutes, and then
Okay.
the rest of it we can save for Friday.
Okay, that sounds like a good idea.
Okay, so I guess you can't see if I can get rid of this. So you can actually see. Look at this and then.
If we use the
Okay.
Englehardt
Yeah.
wall formulation,
Yes.
does that include the simpler cases as automatically?
Yes, it does. You can prove that in the limit where GH bar goes to zero, you're working to leading order. This will actually give you the right answer, the same answer as
That
before.
basically converges to X.
Yeah, exactly. So actually, interestingly, if you work to zeroth order, chi and X are not identical, but the sum of these two quantities is. So it's actually a little bit non-trivial that our prescription is the same as Faulkner-Leibowitz-Moldacena. But it turns out that it is, with the possible caveat about entropy of gravitons that we don't know how to calculate right now. So that's the case that hasn't been checked, the phenomenon entropy of gravitons, but we don't know how to calculate that. So, okay, so here we have, oops, sorry. So here we have the evaporating black hole in ADS. Initially, this is the same as the Hawking picture. It's just a star, it's collapsing. The quantum extremal surface is the same as the classical extremal surface, it's just an empty set, as the case here. And so I've called it rho all, or this is really just rho out of chi. That's the entropy of all the quantum fields down there. Now, here we have the halfway through the evaporation process. And then halfway through the evaporation process, we get a dramatic change, dramatic difference between Faulkner-Leibowitz-Moldacena and mine Aaron's prescription, which is that there's a new quantum extremal surface, which is nowhere near a classical extremal surface, which doesn't exist in this picture. A new quantum extremal surface, it exists a little bit before the page time starts to dominate, right up at the page time. Here, it's a little bit, it's maybe a few Planck lengths behind the event horizon, so it's very close to the event horizon, but not quite at the event horizon. And it has a smaller generalized entropy than the empty set. That means it dominates in the prescription for the von Neumann entropy. And in fact, as we evolve forwards in time, the surface persists and has progressively smaller generalized entropy. And so it exactly gives us the page curve.
So it's inside. that is
It's
to say,
inside, yeah,
it's
but
inside
just
the
barely.
horizon.
Yeah. So in this picture, getting a little messy, but I'll give it a shot. So if we're computing the entropy of boundary time here, T1, let's say, then the quantum extremal surface with generalized entropy, we will compute it, lies somewhere down here, very close to the event horizon. It's almost null separated from that, but not quite. Okay, so let me go through this slide, and then I think we'll pause there. So we have two calculations now, both of them using effective field theory, that compute the entropy of Hawking radiation for anti-de Sitter black holes, large ADS black holes that we actually understand. Now you can do Hawking's calculation. In fact, this is one of the things we did in the 2019 paper to make sure that there's nothing magical in Hawking's calculation that goes away, but it goes through exactly the same way. You know, you can show you violate various inequalities, Iraqi-Lieb and so on that violate unitarity. And we find indeed that the entropy of the reservoir, according to gravity, will just increase up until I guess the thermal value will plateau. Now, of course, that's Hawking's calculation. Still gives you the same thing in ADS that it would have given you in flat space. And there's our calculation in terms of quantum extremal surfaces, which you can find in the semi-classical regime, you can compute in the semi-classical regime, and it actually gives exactly what Page predicted. Not just the fact that it goes up and turns back down, but the literal details of the slope of the curve as it turns over, the time at which the Page transition happens, literally all of that can be computed quantitatively from quantum extremal surfaces. It matches it sort of number for number. It's really, really remarkable. Now, both of these calculations are within the regime of semi-classical effective field theory. You can compute quantum extremal surfaces using effective field theory. So in some sense, this doesn't require a breakdown of EFT because we can just do the calculation in semi-classical gravity. It's just that it's a different calculation than we would have naively thought that we should do in semi-classical gravity. Now, this here is my own prejudice that I'm going to pontificate more on Friday. My interpretation of this is that the semi-classical approximation is valid whenever you have to do only what we call polynomially hard quantum tasks. That means quantum tasks that only take polynomial time in G Newton. If you have to do a quantum task which is exponentially hard in G Newton, then you're in quantum gravity. And computing von Neumann entropy is an exponentially hard quantum task, which suggests to me that the calculation is just wrong, because Hawking's calculation, not because effective field theory breaks down, but because we're trying to compute something with it in a regime where it's not valid. Effective field theory is still valid in that regime is the quantity itself, the von Neumann entropy, which is exponentially hard to compute, that you shouldn't be trying to compute using the standard rules of effective field theory. I'll talk more about that later. The question I'll leave you with today is, why does quantum gravity repackage entropy in terms of quantum extremal surfaces? And we'll talk more about that next time.
All right, let's thank Netta for a beautiful talk. So I had a question, but go on, Ramesh, please.
It's just this miraculous statement you made.
Yeah.
That suddenly a new extremal surface shows up. And it comes exactly at the right time.
Yeah.
It's basically when the entropy of the exterior exceeds the entropy
Precisely.
of the horizon,
Yeah.
right? Is there some way to understand that? Is it that it was always there, but it now separates out? Or is there actually a bifurcation at that point?
Good. That's a good question. Yeah. Yeah. So let me draw a slightly cleaner picture here.
Well, I think actually my question is exactly a precursor question to
Oh,
Ramesh's
okay.
question. So
All right.
maybe you should answer that one, and then we can, because that will explain why Ramesh's question. So the main thing is, how do you actually locate it? You must have a geometry that's evolving, right? So you have a time-dependent geometry.
Yes.
So the question is, yeah, how do you actually locate these extremal substances?
Good. Yeah.
How do you show that they show up there?
Yeah. Good. So
Right, just sort of your question.
draw this a little bit better here. Coupling.
So it's not that the surface settles near the horizon at that time, it's that it doesn't exist before that time?
Precisely. So, okay, actually, it starts to exist a little bit before the page time, but at that point, its entropy is larger than the entropy of the empty set, so it doesn't dominate. There is a switchover at the page time, where now at the page time they have the same entropy, and then once you go past the page time, the new quantum extremal surface has a smaller value of the entropy. So it's, say the page time is somewhere around here. So we have this new quantum extremal surface, and this is the quantum extremal surface for this time, let's say, and then for this time it sort of moves in the space-like direction. So this is for different moments in time here. There would be a different one for each moment in time because the entropy changes. So you could say, okay, it sort of exists before, but this is the first one that actually dominates. Now, how do we locate this thing? So what we have to look for is a solution to these two equations, which were LA and KA are null vectors. I guess normal to the surfaces may be funny in the context of 2 dimensions, but you know what I mean. So how do we look for this? Well, for reasons that I'm not really going to go into at the moment, but have to do with the behavior of quantum field theory, of conformal field theory in flat space, in the way that the rescaling from intervals here to flat space works, we had good reason to believe that this part would be would receive relatively few corrections compared with the classical equation. So we first looked for solutions to this. Once we found solutions to this, we said, okay, let's look in the vicinity of that and see what's happening to the gradient of the von Neumann entropy. And as it turns out, again, from expectations of the behavior of the change in the von Neumann entropy in flat space, we expected that we have to push in towards the black hole interior, because this is satisfied outside of the black hole in the evaporating black hole, is your valid minimal energy condition. We expected we have to sort of push inwards. And then essentially it was just a matter of literally solving the equations in terms of perturbations to these surfaces here.
In the context of spherical symmetry.
So this is 2 dimensions.
Are there, sorry, are you still pursuing this? I was gonna ask.
I think, yeah, there's much more to say on this issue, but we don't have time, so let's move on to a different question.
Are there any physical characteristics of this surface? I mean, is there, if you fell into a black hole, is there anything that you could do? Does it have any?
Yeah, so its
Anything that you
classical
could
analog does. So the classical analog of the classical extremal surface, you would say, okay, if you put a family of observers on the boundary of a classical extremal surface, then and you would say, okay, each one of them measures some infinitesimal area element. What happens as they evolve forwards in time? Then you find that the area is going to decrease whether they move outwards or inwards. So it's the analog of a trapped surface, except it's sort of marginally trapped in all directions. That's for a classical one. Now for the quantum one, it has this S-gen component. S-gen is hard because it involves some entropy calculation. Entropy is highly non-local. And it's, as I mentioned earlier, it's exponentially hard to compute. So there's a sense in which this is an artifact of a large amount of focusing, but it's really so much more than that. We used to think, so Aaron and I have this clause in our 2014 paper where we say, oh, we don't expect that a classical extremal surface, that a quantum extremal surface is ever far away from a classical extremal surface, and so they can be diagnosed from focusing. But this story showed us that that's woefully wrong. The quantum extremal surfaces are very different and highly non-local, and you can't always diagnose them from focusing. You might have one. In fact, there have been constructions of quantum extremal surfaces more recently that have essentially no focusing at all, but the quantum extremal surface still exists. So how do we observe it as individual observers? That's an excellent question. That's probably related to the question of if you were to stand outside the black hole, collect all the Hawking radiation, feed it into your arbitrarily powerful quantum computer, what would you actually get? It's a matter of observation.
I'm afraid I have to stop you.
Yeah. Mhm.
Thank you so much, Netta, for a beautiful talk.